In this session, I welcome every one of you. So as the title mentioned, we are here to understand how to develop a safety critical software or how to develop a real-time embedded software for an automotive application. So first we will start our discussion in understanding what is embedded system, then what are various embedded system that's available in a typical electric vehicle. So I'm taking electric vehicle as a theme and as an example here. So we'll discuss about multiple system that's there, multiple embedded system that's there in the automotive domain. And we'll also understand some of the gap that we see in today embedded system resource development, where our academia is lagging and what is expected in the industry, and some of the myths that are associated in terms of embedded system learning and what is actually practiced in real world. And we'll also discuss more about different job opportunities that's available in the embedded system domain. What is an embedded system? So if you see, embedded system is a kind of a system which has both hardware and a software functioning together, and it basically performs certain computational operation on the given input with the help of a minimum hardware, or you have a minimalistic hardware which is running a dedicated software for doing a specific functionality. If you have all these three things, there should be a specific function, there should be a minimalistic hardware, there should be a dedicated software. If you have this, then you can call that as an embedded system. You can still think of many embedded system that's in and around you. So generally embedded system are programmable. It's basically a low power system, and it has very limited number of peripheral based on its application. So let me move on to different examples on embedded system, so that people who are completely new to embedded system will have a basic idea that what is an embedded system means. So you can consider any handheld device that we see as personal digital assistants now, such as tablets, mobile phones, which contains rich number of sensors, dedicated OS, and GUI based application, and it is basically driven with a SoC or a processor. So this is one of the best example of an embedded system. So other than this, if you get into automotive electronic system, you won't believe me, there are more than 100 plus electronic control units or 100 plus microcontroller, microprocessor sitting there inside your vehicle and doing multiple functionalities such as cruise control, suspension control, airbags, anti-lock braking system, engine management system. Even your engine is run with the help of electronic system. So if you don't have an electronic system in place or embedded system in place, engine in the car will not run. I'm not talking about a very advanced engine that you see in a very new car or in a very sophisticated car. Even a very old Maruti car comes with a electronic fuel injection system. So because now we are seeing this automotive electronic system era, I would say it's more than 2 decades matured. And on the industrial machine side, we have embedded system for automation and embedded system based robotic system. On medical equipment side, we have very complex diagnostic system, which is an embedded system again. And we see surgical robots. So anywhere you see a system which runs a dedicated software on a hardware, it's an embedded system. I hope this is clear. Let me move on. So let's understand some of the important traits of an embedded system. So when I say triads, it's like important quality of an embedded system. Embedded system will contain a minimalistic hardware and a dedicated firmware. So since the software is very closely running on that hardware, or since the software is created for that particular hardware, we call it as firmware. And if you want to study embedded system, it's all about understanding how to write your own firmware for that minimalistic hardware to do the specific functionality that you are thinking. So it is either microcontroller based or either microprocessor based with low power consumption. So that's one of the key requirement trait of an embedded system. So mostly these systems are required to perform under a real time bound. So this is where the topic of today comes. So we are planning to create a safety critical real time embedded system for automotive. Let's say, for example, you have a battery management system which has to uh, identify the health of the battery stack, and actually have to do a very complex way of managing the cell balancing. So all these things comes with a very hard bound constraints. Let's consider a airbag system in our automotive system. So if you have a airbag that's deployed some 5 seconds later, so that's going to help no one. So before the crash happen, you need to have the system in place. So that's what I mean by every embedded system comes with a series time constraint, and generally these systems are standalone or they could be part of a very larger system. So embedded system architecture typically goes on these layered arrangement. Initially you have an hardware. On top of that hardware, you have a dedicated firmware and an operating system running. On top of that operating system, you have an application software. So this dedicated hardware could be a microprocessor, could be a microcontroller, could be a system on chip, could be an ASIC too, or could be an FPGA based system. So altogether, so there is a processing unit that has certain on-chip and on-board peripherals. So that's it. That's what you call it as the embedded, or that lays the foundation of the embedded system architecture as the entire hardware. On top of that, so you have firmware and ATAs. So it consists of the ATAs and firmware layer consists of basic device drivers. When I say basic device drivers, if you have a computer, you would have seen older computer where you have to install necessary drivers for each of the peripheral device. The same way here, hardware that is there on the embedded system have multiple peripherals. Those peripherals require some sort of device drivers. It has to be basically developed as a firmware and has to be imported or has to be targeted on this particular hardware. And along with this peripherals on the device drivers, you have the operating system which enables you the multitasking, multi-threading, and it ideally helps you to meet the timing constraints and resource constraint, budget constraint, all those constraints of your application software. So application software could be a very complex algorithm, could be a very complex computational function, or it could be a very simple a turn on turn off kind of a mechanism. So it depends on your application. So for what exactly you are planning to do or design an embedded system, whether your embedded system is going to be part of a satellite, or it's going to be part of a washing machine, or it's going to be part of a water heater. So that defines your application. So in some certain cases, it could be a complex digital filtering or a complex control mechanism. It could be anything. So now going one level deeper into a typical embedded system structure. So there in the previous slide, we have discussed something called as onboard peripheral, on-chip peripherals. So I have broken down that into a proper arrangement. So initially our embedded hardware will have a processing unit. This processing unit sometimes will have certain ASIC depending on the functionality. ASIC stands for application specific integrated circuits. Then you have analog to digital converter, digital to analog converters. So these are most of the time would be on-chip peripherals tied along with your controller, and sometimes we have onboard peripherals that are connected or interfaced to this microcontroller or microprocessor or SoC based systems. So this input and output devices are most of the time basically called as onboard peripherals because they are not part of your chip, they are away from your chip. So if we look at the different types of embedded system based on the kind of application software that they run, and based on that timing requirement that they have. Now let me derive example from automotive itself with two different applications. So you have a video that's streaming on the dashboard, the vehicle dashboard, which is running the Android software stack. So if you see, it will be running CarPlay or Android or some sort of embedded Linux stack on which you have Qt QML application that's running. These are typically kind of a soft real-time system, or we can even call it as a non-real-time system. But when you have a real-time system, so when I say a real-time system, if an operation has to be happened or should be happening on first millisecond at any cost, it has to be happening on first millisecond. If that misses, it may lead to certain catastrophe, or it may lead to failure of a system. Now let's consider a system like a airbag. So if the airbag has to be deployed before your vehicle sensor senses the crash, or once after the vehicle sensor senses the crash and before the accident is happening, before that your airbag has to be deployed. So it's a hard real-time system. So again, the hard real-time system, if it is for a non-automotive system, so they use a different kind of an operating system, and they use different kinds of systems. If it is pure automotive based systems, people go with a different family or different way of doing the developing the software and the hardware. Software, when I say software, the device drivers and the application part. So that's on the high level understanding or overview of the software architecture. So now we'll get into one level deeper how typically this embedded system, the software architecture will look like. So we have polling based super loops, which is very common, which means there would be one infinite loop that would be continuously running once you power on your embedded system. And inside that, you'll be calling multiple subroutines on a periodic interval. Say, for example, there would be a while one loop or infinite loop. Inside that, you have multiple subroutines or multiple functions that is called on every 40th millisecond, every 50th millisecond, on every fixed periodic interval. So then you have interrupt based software. So these interrupt based software are ideally required for triggering the respective subroutines, which is executed at a periodic rate. When I say a periodic rate, let's say if I want to measure a rotating disk, it could be coming from any application. It could be coming from a motor, or it could be coming from an engine, or it could be any sort of mechatronic system where whenever there is a signal that is coming from that rotation completion, I need to go and count, or I need to go and measure. So it is like whenever there is a request, and that request may come in a periodic rate. I'm not doing it on a polling basis where I'm going and periodically checking. Rather, the request is coming to me. When the request is coming to me, if I serve that particular request, it's kind of a interrupt based software. Then you have multitasking and multi-threading kind of a software, which is quite complex, which require the use of an operating system. So in this strategy, or this particular software architecture allows you to run multiple tasks in a synchronized way using a scheduler that is offered by the operating system. And there will be a task switching strategies that's again, it would be offered by offered as a feature of an operating system. So just to give you a comparison on the when I keep on saying minimalistic hardware, what do I mean by minimalistic hardware? So a typical embedded system will have multiple things, or will have a different set of hardware configuration, whereas a typical desktop or a mobile will have a different kind of a hardware configuration. For example, a desktop system or desktop PC will be having a general purpose or is designed to perform some general purpose application, whereas an embedded system is dedicated for doing some digital control application. And here the RAM range would be in from few MB to mostly in few GBs, whereas here in embedded system the RAM range is in terms of few kilobytes, and you have unlimited energy which is coming from AC power source, whereas here the goal was to reach the necessary performance at the low cost, and it's most of the time it's battery operated, whereas there it's like we have a trade-off between cost and the performance always. So here I'm comparing a microcontroller that's coming from different family at different vendor. If you take a typical microcontroller that are popular in the market, whose address bus width can be either 8-bit, 16-bit, or a 32-bit. So I've compared 3 different series of microcontrollers. So STM32F, which is ARM Cortex M4 or M7 based, will have a typically 12 KB of RAM. If you take a 8-bit controller, which is Atmega 328P, which will have only 2 KB of RAM. And if you consider ARM Cortex M0 Kinetis KL series, it will have 16 KB of RAM. And coming to the ROM, so it's like RAM and hard disk. Here we have RAM and ROM. So ROM would be ideally a kind of a flash memory. So Atmega 328P has 32 KB of flash, and again STM32F has got 64 KB of flash, and Kinetis KL series has got 128 KB of flash. So this amount of flash decides what could be the maximum footprint size of our microcontroller. So this footprint size decides how bigger your application can be. And coming to the energy consumption in the embedded system, so usually embedded system are generally operated by a small battery, and these battery replacement may be problem in most of the systems, because always the systems will come with a pre-installed battery. The system works with recharging the same battery again and again, and many MCU offers low power modes at the hardware level to meet this energy consumption requirement. So on the processing side, so we have 8-bit and 32-bit, 16-bit, ranging from different microcontroller vendors. So how do we select an hardware for embedded system? So I'm just passing here before going to this topic. If you have any queries so far, till what we have discussed, maybe we can embedded system be hacked? Yes, there are possibilities. So that's why we have crypto modules even coming at the level of microcontroller itself. It can be hacked. It is prone to be hacked. So we are working out on certain mechanisms. Many semiconductor industries are working out on multiple mechanisms. So how can we manage after it is hacked? So it cannot be managed once it's hacked, because somebody has already taken the control. What is mean by peripheral? Peripheral is very simple. It is like an external device that we are connecting. So we have an external device and we are connecting it. How is control system related to embedded system? Very nice question. So that's coming from Sushumna. Control system is the end application that's going to run on a embedded system. So just to give you an understanding, if you want to build a control system which controls the speed of a motor, then this control system should be running on a embedded microcontroller to actually perform your motor control operation. I hope all your questions are answered. So let me move on. A typical hardware selection for embedded system is based on this 3 criteria. So we'll consider its processing capability. We will consider the RAM ROM size. We'll do a tool chain and a dock support, and based on the cost. So uh, so if the tool chain is free, uh, I can shell out some money on the hardware, that's okay, fine. Or if even I have to buy a proper licensing thing on the tool side, then it becomes very difficult. And if we have choose a controller which has a very poor documentation support and the cost is also very high, then there is no point in using it. So embedded hardware are usually selected on the following criteria, as I told you. Application latency requirement. Here the term latency means what is the time taken for execution of one complete cycle of the software that is residing in the controller. And application footprint size. Footprint is a term which means what is the total memory size that your executable is taking in your ROM. And cost of the system, that's again what is the total cost. And documentation support and tool chain availability. If you are buying a controller which doesn't have a proper tool chain, so then it becomes very difficult. That is going to improve your production time. So now, if you want to build your embedded system, always C is a preferred language for embedded system. So let's discuss why C is a preferred language for an embedded system. So C language supports many different features, because C is neither a low-level language nor neither a high-level language. Because C supports, or C brings best of both the worlds, I would say. C supports a low-level access through pointers, which allows you to play with the memories, to access the memories. And C is a language that's processor independent, which means the executable that can be created with C can be easily ported onto any different platform. And the data types, C data types are suitable for embedded system because of their portability again. Especially when this data types, what I'm speaking about is C99 data types. So C supports bit manipulation, memory management, and multi-threading features. So all these things combines to make the C language as a suitable programming language for embedded system. So now let me switch my gears to a kind of a different topic. These are so far what we have seen is the traits of an embedded system and how to build a real-time embedded system and what are different real-time application that's there in your vehicle. So for me, on, is it easy to upgrade the embedded system like computer parts? Yes, the answer is, when you say embedded system parts on the hardware side, it is very difficult. But on the software side, now we are seeing advanced features like over the air updates, even that is coming for the system. Even for the embedded firmware, it can be updated over the air. So embedded C means C language used in embedded system. Yes, you're right. There is nothing called as embedded C as such. It's the common C language. We are using certain features of C language for building an embedded system application. So what is the gap in embedded system development when it comes to academia and industry? How does academia is seeing this, and what is really expected in industry? So if you see, there is a huge, I would say, there is at least a 2 decade of a gap that's between academia and industry. Uh, it's there is no point in debating who has to help whom and what is the gap. But if you see on the overall what university covers, or what a typical college curriculum covers, and microcontroller is will study 80, 85, 80, 86, 80, 51. So nothing wrong in starting with this basics, but the point is the microcontroller subject ends with understanding 8051. So it doesn't move further on. And there are very less universities across India, especially, that are covering even how to write a embedded C program, and how to develop your own firmware for a typical 8051 control. Even that's not covered properly. That's not included in the academia as a benchmark. And the C language that we study is C89. It's completely based on C89 standards. So many of the college freshers are really struggling with understanding the other different versions of modern C. At least more than C99 standard, one needs to know C11, C++, 14, 17. These are something that's really expected in the industry now. So if you I've just randomly posted two different job descriptions here. One is coming from a startup, whereas other one is coming from a corporate. So in both the things, it's very clear that the key skill that's required is C, C++, and some of the peripherals that is there in the microcontroller, such as UART, SPI, ADC, timers, GPI, one can. Whereas here also it's the same case. So you require 16 32-bit controllers, serial communication protocol like CAN, SPI, LIN, and an OS like QNX or Linux is required. So when this is what a typical market requirement, and it's very visible that what academia is doing. And so somewhere students are either falling into this category or that category. So they neither master 8051 properly, or they're not meeting some of the expectation that's laid by the company. Rather, many people are thinking that if I learn Arduino, if I learn Raspberry Pi, if I learn Node MCU, I have mastered microcontrollers, or I have mastered embedded system. The answer is no. It's because this is one way of starting to learn the embedded system, but this is again will not lead you anywhere. So I'm seeing students coming from either of this background. People will say that, hey Jagan, I have worked on Raspberry Pi, or else people will say, hey, I have written assembly level program for 8051. But both the things are good to start, but that you should not end your embedded system learning there. What something that's really expected is somewhere in between both of this. So it's very clear embedded system is not about learning how to make PCBs, how to tinker with Arduino and Raspberry Pi. So it's like the real learning will start when you start understanding how to reinvent these platforms. So if you go back and think why Arduino is so popular, why Raspberry Pi is so popular. So these again in turn uses SoC or ARM based hardware, or ATPEGA based, AVR based hardware. But the point is, it comes with a super free, user friendly, community supported library. And nobody cares like what is getting into that library. People are thinking, if I master that library, I have mastered embedded system. So which is a completely a wrong thought. So moving one level ahead, a typical automotive embedded system or embedded software and the skill requirement. So I've classified or I have put the skill requirement over each of the verticals or each of the software domains that's there only in automotive. So in automotive, we have powertrain, we have ADAS, we have application from, or we have electronic and embedded software developed for body control module, or instrument cluster, we have infotainment. So electronics is there, our embedded system is there in all these modules. So people who work on BMS application software development or automatic transmission software development would be using some sort of model-based approach with Simulink state flow and AutoSAR. And people who are working on complete software development for a ADAS module, they'll be working on frameworks like ROS and C++. And coming to the infotainment, it's a complete family of different a different kind of embedded system, which is non-real time, where people work on Linux, Android, and they have their UI design done with Qt and QML. So this is one of the typical embedded system, embedded ecosystem that's there, that goes there inside your automotive industry. So in your automotive industry, we have system engineering, we have system development, and we have system validation. So people generally flow into different category, or people generally grow this ladder in this direction. Somebody would have started their career as a validation engineer, then moved on with development, then moved on with system engineering. But now we are seeing a different trend where we have freshers started getting into system engineering, freshers started getting into our GET started getting into development, even senior members working at system validation. So it's like people are there starting their career on these three phases. So on system engineering side, you have people who are completely working at the architectural level, and they are sharing that information for the application developer and for the base software developer. So base software developer may have tools like AutoSAR and use this tool for building the actual basic software, and people who completely work on the functional software development, so they should be mastering, or they should be the ones who is implementing the control algorithm, which is going to run finally on the microcontroller. And altogether at the end, all these things are verified, validated by a system validation engineer. If you are validating functional software, you take a different approach. If you are validating a base software, you take a different approach. So this is other a different ecosystem for a non-real-time system. So I'm just skipping this. So typically, if you want to do a proper embedded system learning, one can start with this kind of course titles. You need to know embedded C essentials, then you need to have proper understanding of how to do prototyping, embedded prototyping. Then you need to have a proper 8-bit understanding, 8-bit courses, and then you need to slowly migrate to a 32-bit architecture. Then you need to know one real-time operating system. Then you need to have a understanding of embedded Linux. So I have put, so this is one of the template of what are typical embedded learning path, and what kind of projects that you can do with each of the course. So at the end, if you see, if you have a proper embedded portfolio developed, so you will have around 10 to 12 projects or 10 to 20 projects as part of your CV. And you can use this kind of low-cost hardwares when you want to learn embedded systems on your own. So you have low-cost platforms like STM32 microcontrollers. You have platforms like BeagleBone Black, which supports embedded Linux, and you have affordable sensor kit base where you can try connecting many external peripherals to the microcontroller, and you can see how it is working. So the point is very simple. One has to understand or one has to do write code, one programming language, one OS, and one hardware, or one hardware architecture. If you are comfortable with all these, it's good. When it comes to programming language, it should be C or C++. When it comes to operating system, it could be either FreeRTOS or Linux. When it comes to architecture, it is good to stick with ARM and a 32-bit.